This video will walk you through part 2 of classwork 19. Now, problem 4 here, starting with connecting confidence intervals and hypothesis tests. Now, problem 4 is referring to the one sample t-test example from guided notes 17C. So it's referring back to one sample t-test example cell phone about Melanie testing a cell phone ads claim. So if you haven't completed guided notes 17C yet, then please stop and go back and complete it before continuing on with this classwork, or this problem that we're doing isn't going to make a lot of sense. So to refresh your memory, Melanie wanted to test her cell phone company's ad, claiming that it takes 12 seconds on average to download a typical song from iTunes, back when iTunes was a thing. So to do this, to test this claim, Melanie downloaded the same song 45 times from different locations around Los Angeles. And she got an average download time for those 45 different times she did it. She calculated the average and found the average download speed was 13.5 seconds. Okay? So Melanie's download time was 13.5 seconds versus the ad claimed that the download time should be, on average, 12 seconds. So let's go ahead and conduct this one sample t-test in JASP, and then we'll consider what the result means and what the confidence interval is telling us. We'll see that a pattern emerges connecting confidence intervals with the results from our hypothesis tests or significance tests. So here we are in JASP. This is the data set showing the 45 download speeds. So we can see each one of these represents downloading the song one time. How long did it take to download the song in number of seconds? So the first time, 12.9 seconds, the second, 10.9 seconds, the third, 11.6 seconds, and then a lot slower, 14 seconds, and so on. Okay. So we can see all 45 download times here. Now we want to conduct a one sample t-test, and to do that we start by going to t-tests and click on the drop-down menu. We want to do a one sample t-test. We're going to use this one at the top. You can ignore Bayesian stuff is advanced statistics, so we're just going to ignore all of those in this class. So we're going to select this one sample t-test, and that opens up our dialog box. Now, Part A of number 4 says conduct a one sample t-test by going to t-test, one sample t-test. What would the appropriate null hypothesis be? And what should go in our test value box? So keep in mind that when we run a one sample t-test in JASP and in most stat softwares systems, we will default to putting the test value of 0 in. So let's think about what this test value means for us here. What it is saying in this case is, so if we were saying, okay, I'm interested in how long it takes to download the songs in seconds, so that's my variable of interest, happens to be the only variable in this case, in this data set. What this one sample t-test is testing is, does it take a significantly different amount of time to download a song than 0 seconds? Does it take significantly longer to download songs than 0 seconds? Of course it's going to take significantly longer than 0 seconds. It's not an instantaneous thing. We know that downloading takes at least a little bit of time. So it doesn't make sense to have 0 here because we're not trying to test, does it take longer than 0 seconds to download a song? Right? We want to think back to the problem. What was Melanie trying to test? And what she was trying to test was the company's advertisement claiming that the average download time is 12 seconds. So what we want to do is, we don't want to say, okay, did it take her significantly different or significantly longer to download those songs than 0 seconds? We are interested in testing, the company's claim of 12 seconds. So we're going to go ahead and put the 12 in our test value box. Okay. And then if we click out of it, you'll see it updates our results. For all tests, the alternative hypothesis specifies that the population mean is different from 12, right? So that's telling us what test value we put in there. And this makes sense because we want to know, does it take a different amount of time than 12 seconds, which is what the company claims. So we also want to go under additional statistics and click location parameter. And this is going to give us some additional information, right? So if we take this off, you'll notice we start with just the basics, the t value, the degrees of freedom, which in a one sample t-test is equal to n minus 1. Our n was 45. And our p-value, or our significance. If we select location parameter, now it adds this mean difference, and we're going to talk about that in a second. What is that mean difference that it's talking about? Now we also want to select confidence interval 95%. I'm going to move this over just, nope, can't. And you'll see that it adds the 95% confidence interval for the mean difference here. Now, something that's also going to be very helpful for us is clicking on descriptives. That's going to give us our n, our mean, our standard deviation, and our standard error, which hopefully by now we're starting to remember is the standard deviation of the SDOM. Okay, so we've clicked everything we need to click in here, so let's go ahead and look at our results. So we see this bottom table, the descriptives, this is summarizing some of the information we already knew. She downloaded 45 songs. The average was 13.498 seconds. We rounded it up to 13.5. And we can see that on average, that download speed time varies by about 3 seconds. So she got the average speed of 13.5, but it varies on average plus or minus about 3. So maybe like 10.5 to 16.5, right? So something around there would encompass our one standard deviation, which is about 2/3 of our data. Now, the confidence interval is telling us something a bit different here. So let's see. Before we move on to that, I'm looking back at the classwork here. I see, so based on these results, let's take a moment and consider, would we reject or not reject the null hypothesis? So in this case, let's just clarify that our null hypothesis would be that the mean of all of the download speeds, right, for this whole population is equal to 12, because that's what the company claimed it was. The alternative then is going to be the mean is not actually equal to 12. It's equal to something else, right? Maybe slower, maybe faster, but it's not 12. So based on our results, would we reject or not reject the company's claim that it takes on average 12 seconds to download a typical song in Los Angeles? So looking back at our result, we want to look at our p-value here. The p-value is what's going to tell us whether we reject or don't reject our null hypothesis. So as a reminder, if our p-value is less than, right, that's less than 0.05, this is the case where we reject. If p is not less than 0.05, so if it's equal to or bigger than 0.05, then we do not reject. So looking back at our result here, we see our p-value is 0.003. So I'm just going to write that down. P equals 0.003. So where does this 0.003 fall? Is this bigger than 0.05 or smaller than 0.05? And something that tends to throw people off a lot of the times is we'll have 3 decimal places here, but we only have 2 here. So let's say you're comparing 2 decimal places with 3 decimal places. You always want to line up the decimals together, and you can imagine there's like a invisible 0 there, right? So you want to look, okay, we've lined up our decimals, 0 and 0, those are the same. We can't answer which one's, whether it's smaller or bigger yet. 0 versus 5. Well, 0 is definitely less than 5. So in this case, our P of 0.003 is less than 0.050. In other words, our p-value is less than our alpha level that was set. So if our p is less than our alpha, then we are going to reject the null hypothesis. In other words, this is significant. It would be really weird for Melanie to get a sample with a mean of 13.5 seconds if it really only takes 12 seconds on average. That would be so weird that we don't think that this is true. We think probably it's not equal to 12. Okay, so we conclude that we would reject the null hypothesis. It is significant. Let's look at that 95% confidence interval for mean differences, or mean difference. So we can see in our output, I'm just going to abbreviate this, the mean difference. That's not a technical abbreviation, it's just for right now. Is equal to 1.498. And the confidence interval, the 95% confidence interval, because we could have different levels of confidence. Okay. For the mean difference was from 0.536 to 2.460. So here's our confidence interval of the difference written here. Well, what is this difference that we're talking about? Because these numbers, 1.498 and 0.536, 2.460, those don't seem to connect very well with my problem when I was talking about 12 seconds and 13.5 seconds. So this difference that's being referred to here, this difference is between our hypothetical unknown population, right? There is some mean of this actual population of downloading all the songs, the actual average it takes to download a typical song in LA. So this, of course, is a question, but we were taking the company's word for it that that should be 12. Now, Melanie went and she collected her data set and she got, let me erase that. She got the mean of her data set, her sample, was 13.5. So this difference that we're talking about is the difference between our hypothetical population, what we're trying to figure out, and our actual sample here. And we know that looking back at JASP, this is actually 13.498 if we're getting down into the details. So what is this mean difference? That's the difference between our sample, 13.498, and difference means subtract, and our hypothetical population, which in this case, we were basing it off of what the company said which we had 12 seconds. If we subtract, we see this is the mean difference that it's referring to. Okay. So let me go ahead and clean this up and redraw a little. Give me a second. So this confidence interval is saying that, okay, we have the hypothetical population with some mean, and then we have our sample. If the null hypothesis is true, then really those two things should be right on top of each other, right? We're saying they have the same mean. The population and the sample have the same mean. Okay, so we're talking about the difference between those two groups. So when we're looking at this confidence interval for the mean difference, if those two curves had a mean difference of 0, if they were right on top of each other, if the null hypothesis was true that the mean really is 12, then what mean difference would we expect to see here? Well, the difference between the blue and the green is nothing. They're right on top of each other. If the green one and the blue one, if they both are 12, then this mean difference would be 0, because 12 minus 12 is 0. Okay, so this confidence interval for the mean difference, this is saying how far apart do we really think those two means are based on our data? What this is telling us is that we think that those two means of our hypothetical population and of our population based on our sample, we think the means are different by at least 0.536 seconds, by at least half a second. We don't think they're super different though, because we don't think that they're different by more than about 2.5 seconds. So we're saying that the difference between our two means, our hypothetical mean, our sample mean, this confidence interval is giving us how much difference we think there is between those means. So we think that there's at least half a second difference, but not more than 2.5 seconds difference. So what important value is not captured by this interval? Keep in mind the null saying this. If the null is true, those two curves are essentially the same thing. They're right on top of each other. And we would expect, if the null is true, we would expect a mean difference of 0. Is 0 in between these values that we got for our confidence interval? Does this interval contain 0? So if we were to write this out on a number line, right, we've got 0, 1, 2, 3, we could do -1, right? So 0.536, that would be a little in between the 0 and the 1. That'd be about here. 2.46 would be a little less than halfway between 2 and 3. So that'd be here. So we're looking at the interval right here. We think the true mean difference between that 12, that claim of 12, and the real population average is somewhere in this interval. We think they're at least this much different and at most about that much different. Notice that 0 is not in this interval. It's outside of the interval. If that 0 were inside, right? So if the 0 were actually inside our interval, then it wouldn't make sense to reject our null. We're saying, well, if the null is true, then the mean difference is going to be equal to 0. We are rejecting this claim. We're saying we don't think it's actually that. So it makes sense that 0 is not in the interval that we think really is the difference. So what is the pattern? If the p-value from the one sample t-test is significant, so if our sample was sufficiently unlikely to have come from the null population, right? So if our p was less than our alpha, and meaning it's significantly weird, then would we expect to see a 0 in our confidence interval of the difference? If we're saying, no, it's so weird, I'm going to reject the null, then we should not, then the CI, confidence interval, should not include 0. The reason for this is because it's significant, meaning we reject the null. So the mean difference, basically we're saying, can't be 0. Right? If we're saying the null is not true and we're rejecting it, then the mean difference can't be 0. There has to be some difference there. If the p-value from our one sample is not significant, then should the confidence interval of the difference include or not include 0? In this case, the confidence interval should include 0. This is because we're saying if it's not significant, we're saying, yeah, it could be the case that the mean is actually 12. And if it is the case that the mean is actually 12, then the mean difference between what from the true mean and from what we expected is 0. So yeah, our confidence interval should include 0 if we think the null could be true. So finally, let's summarize. What is the relationship between one sample t-test and confidence intervals? So with a sample t, right? So here we want to kind of establish what's happening in each of these cases. So significant meaning p less than 0.05, significantly weird. And this one, no, not, it could be the null. Not weird enough. So here, sample t. So keep in mind, it's asking, is it inside or outside the critical values? Well, our critical values, keep in mind, are the ones that cut off our rejection regions in our tails. So my sample t, if it's significant, would it be in the inside do not reject region, or would it be in the outside reject region somewhere? In this case, we would expect it to be outside, right? We would expect to see our sample t somewhere out in one of those tails. When it's not significant, then we would expect to see, right? If it's not significant, then we're saying, well, it could be the same as the null. So we would see this inside, do not reject. So here, if it's not significant, our sample, oops, let's go back. then our sample t will be inside our critical values. If it is significant, our sample t will be outside the critical values. Now the confidence interval, when it's significant, does that mean that it should contain the value that we're testing against or not? Right, and this has to deal with this idea. Okay, if it's significant, that means we're rejecting the null. If we're rejecting the null, then it doesn't make sense for the confidence interval to include the null. Right, so in this case, the confidence interval does not contain that null value. And when it's not significant, we would expect that it does contain it. Right? Or in other words, we would expect the confidence interval for the mean difference to not contain 0 if it's significant, but yes to contain 0 if it's not significant. Okay, if it's significant, what do we do with the null? If it's significant, that means we are rejecting the null. That's that symbol for the null again. If it's not significant, we do not reject the null hypothesis. Here I kind of gave us our hints over here already. So when it's significant, this is when our p-value is less than 0.05. It's less than our alpha. If it's not significant, then that means it's not less than alpha. It's bigger than or equal to 0.05. And then finally, if it's significant, would we think that it's the same as the null or different from the null? Would we expect that population mean that we're really looking for? Do we expect it to be the same as the null or different? If we're rejecting the null because it's so weird, then we would expect it to be different. We would expect the true population mean to be different from the null value. If it's not significant, we expect that population mean could be equal to the null value, so not different. All right, hopefully that clarified some things on connecting null hypothesis with testing with confidence intervals and then seeing it performed in JASP as well.